Welcome back, Wisdomers. Today we are diving into the mathematical foundations of our very first machine learning model, linear regression. In this video, we will explore the derivation of the loss function, a concept that serves as the bedrock of your entire AI journey. This is one of the most critical lessons in this first section. I encourage you to stay focused until the end and revisit this video as often as needed to master these fundamentals. To better understand mathematics, let's refresh the concepts we learned previously with an example. Take a look at this dataset. It contains one input feature, bill amount, and an output feature, tip amount. The data is represented in a two-dimensional coordinate system. The goal of a machine learning model is to find the equation of a line that identifies patterns in a dataset. Assume our model has identified the equation y equals 0.18x plus 0.2. We can now use this line to predict future data. For example, if the bill amount is x equals $7, substitute it into the equation y equals 0.18 times x plus 0.2, which gives us y equals $1.46. Now we come to the real challenge. If you look at the graph, you'll realize that there are actually an infinite number of possible lines that could capture the patterns in our data. We've only highlighted 2 lines here to keep things simple. This brings us to a fundamental question in machine learning. Out of all these infinite possibilities, how do we identify which line is the best one? Before we dive into the mathematics, if you find this content helpful, please consider subscribing and sharing it with others. You can also visit our learning platform at www.wisdomers.in to access interactive quizzes and hands-on projects. To identify the best line for our dataset, we must employ a mathematical approach. We will use specific calculations to evaluate and finalize the line of best fit. The mathematical tool used for this purpose is known as the loss function. In the field of artificial intelligence, the loss function is a fundamental concept, so please stay focused as we dive into the details. To truly grasp the concept of a loss function, we will work through a practical example before deriving its formal equation. Let's return to the 2 candidate lines we previously visualized. y1 equals 0.18x plus 0.2 and y2 equals 0.16x plus 0.8. We will now perform the necessary calculations to determine which of these lines provides the most accurate fit for our dataset. Let's walk through the step-by-step calculation of the loss function. We begin with the bill amount, x, and the actual tip amount, y. First, using equation 1, we generate our predicted values, y1. By substituting the bill amount from our dataset into the equation, we obtain a predicted value of 2.0. To determine the accuracy of this prediction, we calculate the loss, which is the difference between the predicted value and the actual value, y1 minus y. We then square this loss to eliminate negative signs and ensure all loss values are positive. After repeating this process for every data point, we find that the final sum of all squared loss values is 0.80. Similarly, we repeat this entire process for the second line equation, which gives us a total loss of 1.20. After calculating the total loss for both lines, we can compare the results. Since line 1 yields the minimum loss, 0.80, compared to 1.20, it is identified as the line of best fit for our dataset. Stay focused, Wisdomers. We are now going to take a final look at the formal loss function equation. and explore its graphical representation. Our equation is defined as the summation from I equals 1 to n of the squared difference between the predicted value y hat and the actual value y. Here, n is number of data points in our dataset. If you observe the graph, the small vertical segments represent the distance between the observed data points and our prediction data point on the line. This is exactly what we mean when we talk about loss. One final crucial point to consider: if we only use the total sum of squared errors, the loss value will naturally increase as the number of data points increases. To ensure our loss metric reflects the average loss rather than just the sample size, we normalize the equation by dividing the total by n. This gives us the formula 1 over n times the sum from I equals 1 to n of y hat minus y squared. This is what we call the mean squared error, or MSE, the mean squared loss function. In our next session, we will develop a deeper understanding of this equation and its graphical properties.